Hey everyone, this is Avi, and today I'll be talking about my project titled Developing an AI Assisted Mobile App to Improve Polypharmacy Management. To start with a little bit of background, polypharmacy is defined as the regular use of five or more medications by a patient. While it affects multiple populations, in the US alone, over 65% of geriatrics, or adults aged 65 or older, are affected by polypharmacy. As of 2022, this amounts to 37.8 million people, and by 2050, it's projected to account for 53.4 million people. There exist many challenges to polypharmacy management. In addition to having complex medication regimens, many patients are faced with having to manage their medications without any assistance at home. In addition, age related changes such as memory difficulties or poor eyesight may create further barriers for them. And then there's also just human error. Imagine how hard it is to manage medications that would need to be taken at different times, in different ways, at different doses each and every day. All of these different barriers lead to medication mismanagement, including dose alterations, additions, discontinuations, and accidental restarts of discontinued medications. These changes can lead to many adverse outcomes, such as treatment failure, unwanted drug effects, hospitalizations, and even death. So, what is the current solution to this problem? Unfortunately, what we have is pretty limited. We have systems of reminders and alarms, we have apps that will log and track medication adherence, and even websites where you can type in the engravings on the side of a pill along with its color and shape to manually identify what it is. And yet, there are absolutely no tools to proactively prevent medication errors. That is the gap that my team and I were attempting to address. Our solution was to combine these existing tools with image recognition AI technology to develop a phone application that would function as a virtual home care nurse and allow users access to real time pill identification and verification. To create this application, we first trained machine learning software using 597 standardized pill images taken from an NIH database. The model was then refined using a secondary database of 100 non standardized images compiled from Google, as well as photos that we took ourselves. The images were manually annotated using a software called CVAT. By manual annotation, what I mean is that each colored box that you see on these images was individually hand drawn and allow us to classify each pill as number one, a pill, but then also by its color and by its shape. This is how the model was trained to identify medications. The diagram here shows an overview of the training data, which shows how the annotations help to differentiate between pills using various characteristics. As you can see, each pill is labeled as a pill so that it can be differentiated from other objects that might be in the background of the picture. It is then further classified by its shape, such as round, rectangular, or elliptical, and then by its color. This means that, for example, if I add ibuprofen to my medication schedule, it would be stored as a pill that is round and red instead of just being labeled as ibuprofen. The front end of this app was designed using Flutter, which allows us to build an app that could be used on both iOS and Android phones using the same code base. Google's material design was used for streamlining the design process and to create the user friendly interface. The back end was written in Python and hosted on Microsoft Azure Cloud, and data storage was also hosted on Azure. Firebase authentication was used to provide users with a secure and convenient sign up process when they were creating their profile on the app. Validation testing was performed using an additional 124 images, and our analytics showed that even being trained on just under 700 images, the model performed at a 85% accuracy. That's actually pretty good. It should be noted that with the post-processing heuristics, this accuracy actually goes up even a little bit more when it comes to real-life usage. Once the model was built, we switched to focusing our attention on building a simple user interface. The users first open the app, and they are met with the home screen, which shows their daily medication schedule. In order to add a new medication, users are instructed to take an image of their pills on a plain background. They then label the medication using its name, its dosage, and the reason for taking it. The machine learning software uses the image that the user takes of their pill to learn what medications are in their med list and differentiate between them. Users also have the ability to set a schedule for their medication, including the time at which they're supposed to be taking the med and the number of pills that they are supposed to be taking at that time. Then, when viewing their medication list, users are also able to see a real-time count of their remaining pills. The app notifies users for two instances. First, users are notified when it's time to take their medications. Then users are also reminded to refill medications when their pill counts are getting low. Now, to get on to the exciting stuff, when it's time for users to take their medication, the app instructs them to snap a picture of all the pills they plan to take together on a flat surface. The app assesses which pills are present and then gives users real-time feedback that details which pills are correct, which pills are missing, and which pills are unexpectedly there. So in this example, you can see that the app expects to see the user taking 2 ibuprofen and 1 vitamin D pill. It reports back that the user correctly has one of the ibuprofen pills and one of the vitamin D pills. However, they seem to be missing the other ibuprofen pill and have also unexpectedly added a Benadryl to the mix. At this point, the user can go back, fix any errors, and then re-verify the pills before actually taking them. Once the pills are marked as taken, the home screen will adjust to show this. In this example, the green check mark shows which pills have been taken correctly, the blue shows which pills were missing, and the red shows which pills were unexpectedly taken. The app also allows for historical adherence tracking using a calendar feature. Finally, the app also has an as-needed pill identification feature. This feature allows users to take a picture of any misplaced pills and have them be identified by name and dosage. So, in conclusion, our application was able to combine traditional medication management with machine vision technology to create a completely new polypharmacy management strategy. We were able to tackle the key limitations of existing solutions by using computer vision integration for real-time medication verification and proactive error prevention. At this stage, our app is a successful proof of concept. Next steps would be refining the machine learning using tens of thousands of images to increase accuracy, and refining the user interface to further increase the ease of use. Its accuracy and precision would then need to be verified by clinicians and pharmacists in preclinical testing, and then afterwards, there's also a need for end-user testing prior to releasing the finalized product to market. This project wouldn't have been possible without the collaboration of multiple entities and people. I would like to give a special shout out to the Blue Cross Blue Shield of Michigan Foundation for providing the financial support for this project through its Student Award Program research grant. Thank you for your time and have a good day.